up to now, we've mostly focused on concepts. I've talked about the concept of thread pools. I've talked about some of the interfaces that are defined. We talked about some of the concepts related to execution policy and policy configuration, blah, blah, blah. So now it's finally time to take a look at some code. And we're going to do this in the context of a PrimeChecker app that uses the Java Executor interface and a fixed-sized Threadpool implementation. And this is intentionally designed to be a very simple app. So this app demonstrates how to use the Java Executor framework to check if n random numbers are prime. So you get to give n, in this case n is 25, and it will then generate random numbers, and it will check them to see whether or not they're prime or not. And it's going to use a pool of threads to do this. I suspect you probably all know what a prime number is, but just in case you blanked out on 5th grade math or whenever you learned that, it's basically a number that is divisible only by itself or by 1 is considered a prime number. And obviously there's a lot of them, and they get very large. These are just some of the early ones. You get to select through the GUI of the app, it's an Android app, the number of prime numbers you want generated to check for their primality. And then you can also start the app running. So when you click this button, it's called a floating action button, it'll start the app running. And there's a couple interesting properties that the app has. First, it's embarrassingly parallel. So that means there's no data dependencies between running tasks. Computing prime numbers has no dependencies. You can compute n prime numbers in parallel, where n is probably best pegged to the number of cores on your processor, because this is a compute-bound task. Computing prime numbers is compute-bound, not I/O-bound. And that's what's called embarrassingly parallel. The example I always use for embarrassingly parallel, because I like human-known examples that help you intuitively understand the concepts, is a bunch of washers and dryers, where you can do your loads of clothes to wash them and dry them in parallel, right? So if you're like me, when I was in college, I would not wash my clothes for a long time, so I'd have a huge pile of clothes, and I would go down to the laundromat and do like 7 loads at a time or whatever. So that's embarrassingly parallel. Secondly, as I mentioned, these tasks are compute-bound. So the time to complete each of these tasks is dictated by how fast the cores run. So assuming we have 4 cores, then we probably, assuming we want to use them all, we want to have 4 threads in our pool that can be computing all of these different tasks at the same time. I really like this visualization, by the way. This is cool. So that's what I use to indicate CPU-bound stuff. The actual computation of whether or not a number is prime, the determination of whether a number is prime, is performed by this method called isPrime. And this method is intentionally designed to be inefficient. So it's just using a brute force algorithm that checks to see whether or not a number is prime, by checking to see if it can be divided evenly. This, as you can see, is a compute-bound algorithm. So there's no I/O calls, there's no going and reading or writing from files, or reading or writing from the network, or going and accessing a database or whatever. It's totally compute-bound. And it's intentionally designed to be inefficient. It'll return the smallest factor if the number is not prime, and it returns 0 if the number is prime. And the goal of this whole thing is just to burn CPU time, thereby demonstrating the benefits of parallel processing. Because if you have more cores, then you can do the computations in parallel. And even if one takes a long time to run, because if you have big numbers, it takes a while to determine whether it's not prime, those things can run in parallel. This particular implementation uses a fixed-size executor thread pool. And it uses the executor's new fixed thread pool. And this creates a fixed-size thread pool. You can see it has a fixed number of threads. Once you set the number of threads, that's the number of threads that will continue until you shut this thing down. And that turns out to be very hard to do because the executor interface is so simple, there's no way to shut down the underlying thread pool. So we'll come back and talk about that later. That's a very important issue to wrestle with. So this is really only good if you have thread pools that run sort of from the point when they're created to the end of the whole program altogether. We select, for this particular use case, the number of processor cores to be as many available processor cores as is known to the Java execution environment. So there's a method in Java called runtime.getRuntime.availableProcessors, And that gives you back the number of cores. I know it says processors because when Java started out, there were really no multi-core chips. There were multi-processor systems. But now this gives you back the number of cores. And it also gives you back, just for point of reference, the number of virtual cores. So many multi-core machines nowadays will have, like my machine here has 8 physical cores, but they're actually virtual cores. So it thinks that I have 16 cores. A virtual core is just a hyper-threaded core that can do some instructions in parallel, but it's not a fully separate core. It's probably more information than you need to know, but just FYI. So this tells us let's make as many threads in our fixed thread pool as there are cores on our system. And we do this because the isPrime computation is a compute-bound task. If this was an IO-bound task, we would do something different. We would use that formula I talked about the other day in class where you have n times the quantity 1 plus wait time divided by service time. That's another computation to figure out the number of cores if you have IO-bound tasks. But we don't have IO-bound tasks here. Now, we have a user interface thread, and this is what you get out of the box with Android. All Android apps start out with something called a UI thread, and that's where the, quote, main activity runs. And it's going to generate random numbers in the user interface thread after it's directed to do that by the user. And then those random numbers are then queued up and given to the executor implementation. So we're going to have a queue of tasks, which of course are implemented by runnables. And when you call execute and pass in a runnable, that goes ahead and puts something on this work queue. You don't actually see the work queue. That's hidden from you by the implementation of a fixed thread pool. And also, just as a point of reference, the fixed thread pool uses an unbounded queue. So that will grow and grow and grow and grow and grow until your system runs out of memory. Your virtual machine or your execution environment runs out of memory. And it does this to avoid Threadpool-induced deadlocks. If you want more information about Threadpool-induced deadlocks, take a look at this link. You will end up potentially with Threadpool-induced deadlocks if you have a fixed size number of threads, a fixed size queue to queue tasks that are waiting to run, and there's various callback scenarios where you end up with deadlock on yourself. So to avoid that, they use an unbounded queue. Now that means that you can end up chewing up a lot of memory if you're creating tasks faster than your cores can process them. But we don't have that problem here. So this is what the main activity looks like. There's a method called start computations when you click the floating action button on your phone. That's the method that gets called back. And what that does is it goes ahead and it generates count random numbers, count being whatever you gave as the count. Let's say 25, just to be concrete. And these random numbers are generated in the range of some S-max value. Let's say that that's a million, just to be concrete, or 10 million, something like that, minus count up to S-max value. So we're going to generate a bunch of values within this range. And we do this, oh, here we go. I say what it's set to a large value. Actually, I guess that's a billion. 1 billion random numbers, just like Dr. Evil from the Austin Power movie. I don't know if you've ever seen that, but it's a funny movie. So, and we do this so that we end up with duplicates. We want to generate duplicates, and you'll see why we generate duplicates later. Each random long that we generate here, for each of the random longs that we generate, we're then going to go ahead and say, hey executor, hey fixed size executor, please execute this computation being a new PrimeRunnable that's going to pass in the random number, each of those random numbers, and that'll basically enqueue it in the Threadpool executor such that when a thread is available in that pool, it'll go ahead and take off the next random number and check to see whether it's prime. And we'll talk about that PrimeRunnable class in more detail momentarily. Here's what PrimeRunnable looks like. PrimeRunnable is a class that implements runnable, which means it's got a run hook method down here. Its constructor stashes away the main activity. That's so we can do some user interface stuff from a background thread. You'll see how we do that in a second. And we also keep track of the prime candidate. That's what PC stands for. So we store those two things here. Here's that isPrime method we looked at before that does the brute force computation to see if the number's prime or get its smallest factor if it's not. And then finally, here's the run method. This is what gets called back in a thread in the Threadpool, right? So when it's ready for this PrimeRunnable instance to be executed by the executor framework, the run method will get called back, and it's going to call the isPrime method on the prime candidate and return the smallest factor, and it'll print out the results. So although there's going to be a lot of PrimeRunnable instances, let's say that we set that to 100 or whatever, some large number, or 1,000, they will run on a much smaller number of threads. And that number of threads, of course, is based on however big you made that fixed-size thread pool. So we could have hundreds of tasks to run, but only 4 threads to execute. So that's kind of the beauty and joy of the executor framework, is allocating memory to hold prime numbers is way, way, way more memory conserving than allocating that many number of threads, because each thread would be gigantic, because each thread takes up at least a megabyte of virtual memory to hold the stack and all the other resources that the thread has to keep track of in order to run. So that was an overview of the PrimeChecker app. We will talk in a moment in the next part of the lesson about the pros and cons of said PrimeChecker app. So this was just giving you an introduction to kind of how you use the pieces in the executor framework.